Okay, let's get started. Good morning, everybody. Um,
Good morning.
so, did you get any chance to look at the class lecture 3 that I uploaded?
I was actually rewriting everything down on a notebook. Never got the chance to do it.
Okay, okay. So, let me share my screen. Can you see my screen? Like source free series RLC circuit?
Yes.
Yes.
Okay,
Yeah.
thank you. Uh, then, as I mentioned in the email, so everybody please try to understand well today's class and you will be looking the previous classes. So based on these two classes, by end of today, I am going to assign you first set of homework. Still, I did not upload. I will be uploading, and then I am going to send out an email to you. And the due date to submit this homework will be next Friday. This means August 20th. So you will be getting a week. So you will be fully fine. You might see 5, 6 problems, numerical problems about this source-free series circuit or parallel circuit, very similar problems that we are discussing in the class. So everybody please understand the lecture first and then try your best to solve the problems. Uh, I will create a Dropbox on eCourseWare, and for example, Dropbox title will be homework set on. There you all will be uploading your homework just on single PDF file. That will be fine. Okay, so everybody say, I mean, in the last class we discussed source-free parallel RLC circuit. Today we will be discussing source-free series circuit. So as you can see, so again in this case, the assumption is that there is a source connected and suddenly the source has been disconnected at time t equal to 0. So that's why this has been the source-free circuit. But what is the impact? What is the dynamics? What's the characteristics of this circuit that we want to look at? So because the source got disconnected, but inductor and capacitor has stored energy. So therefore, because they stored energy, that's why there are initial condition. So right side look, the initial condition at t equal to 0, I naught equal to capital I naught. This means this I naught is through the inductor. Basically, this is the same current, but current related to the inductor. And then what is the voltage across the capacitor? That is V naught, I say integration minus infinity to 0, I dt, that is capital V naught. This means we are assuming current is capital I naught and voltage is capital V naught at time t equal to 0. Now, based on these two initial conditions, we have to find out what is the current expression. And based on that, we can determine what is the type of the response. Is it overdamped, underdamped, or critically damped? I mean, exactly similar or the same type of analysis as to the source-free parallel circuit. Just the difference, this is series circuit. Last class we discussed parallel circuit. Okay, so now moving forward, everybody see that circuit. Now in that circuit, we are applying KVL, Kirchhoff's voltage law, around the loop, and then see equation 1, Ri, that is the voltage drop through R, then IC integration T naught to T I dt. This means that is the VC, voltage across capacitor, and then L di by dt, that is for the inductor. That equals to 0 because there is no source. So we are applying the KVL. So that's equation number 1. And again, similar to the previous case, parallel case, because there is integral sign, the middle term is integral. So we want to eliminate that integral term. So how to eliminate? We have to differentiate. We have to making derivative with respect to time. So we are doing that and then rearranging the terms, we got this equation. You see that r for I di by dt, and then the integration I dt, if you make derivative, then it will come back to I. So 1 over c multiplied by I, then L d square I by dt square, that equals to 0. And then again, I am rearranging. At first, I am taking the second derivative term, d square I over dt square, and then r over L di by dt plus I over L say 0. That is equation number A. I think everybody could follow this one, right?
Yeah.
Yes.
Yes.
Okay, great. Yeah. So then, I mean, similar to the previous situation, that equation A is clearly the second order differential equation because there is d square I over dt square. Now, what I am doing from now, so from equation 1, look the topmost equation. So that is the general equation at time t. But at time t equal to 0, what I am doing? So look equation 1 and then the expression that I'm showing here, r I naught plus L di naught by dt, third term. And then for the middle term, 1 over c integration of t naught to t I dt, that is basically the voltage V naught. Therefore, see the previous slide, see the last initial condition, V naught 1 over c integration I dt, that is capital V naught. So because this is the initial condition, that's why here for the middle term of equation 1, I'm replacing it by capital V naught. And then from there, my goal is to find out di naught over dt. Therefore, see everybody, this is just the simple calculation. And then V naught and Ri naught is getting right side, so minus, and then I am dividing by L. And then this is very useful for initial condition to solve the numerical problem for the series circuit. You remember that last class I was showing you one similar calculation which was dV naught by dt. There was one expression and we utilized that to solve the problem. In case of series circuit, we have to utilize this last expression. So therefore everybody just keep in mind. Soon today I will show you the problem, then you will get it. So, I mean, you can take a note in your notebook that we need to use this initial condition to solve numerical problem. Okay, now moving forward. So because that is that second order equation, so what is the solution? We have to consider the solution of equation A is I equals to A multiplied by e to the power st, where A and S are two constants that we need to determine. I mean, similar to the previous situation. So therefore, from A we have, so A means you remember this equation. This was the A, the second order equation. So after substituting I equals to A multiplied by e to the power st, then we will be getting this one. And then you see in this equation, the common factor is A multiplied by e to the power st. So you are getting AC square plus R over LS plus 1 over LC. And then again, this multiplied by this equals to 0. So this can't be 0 because that is our assumed solution. So the right side factor, this factor is the 0. And then everybody says, so I have given the name C, and this C equation is a quadratic equation. Therefore, S will have two values, one with the plus sign, other with the minus sign. Exactly the same thing that we did. So now what is the solution of S? Look this one. Yes, exactly that one. S equal to minus B plus minus root over B square minus 4AC over 2A. So do you understand what I am telling? Like last class, I was telling you that quadratic equation ax square plus bx plus c equals to 0. Then x is in numerator minus b plus minus root over b square minus 4ac and divide by in the denominator 2a. So exactly. So from this equation, from that c equation, exactly I am applying that one and I am getting this expression. And then this is the next line. I just reorganized. So finally from here, because there is plus minus sign, accordingly I am getting two solutions. One is S1, other one is S2. So you remember in case of parallel circuit, we also derived similar two expression for S1 and S2. But those were probably it was R over 1 over 2 R say. Probably it was like that. Yeah. But in this case, it is R over 12. R over 12. So then again, you see right side, if you change R over 12 by alpha, which is called Nepper's frequency or damping coefficient. So in this case, alpha is R over 12. And then for 1 over LC, it is called the resonant frequency or undamped natural frequency. Unit is radian per second, 1 over root over LC. So this means this equal to minus alpha plus root over alpha square minus omega naught square. And then similarly, the expression for S2 goes. I think everybody is understanding, right? So exactly the similar thing we did in the last class.
Yeah, this makes sense. I'm just
Yes.
Okay.
where you're going from creating the differential equation and solving for the solution. I was wondering, do you like? I was trying to the last lecture. What I was doing was I was trying to go through and try to solve it through a Laplace transform, and some of the stuff wasn't really making sense. But we don't have to go over that right now. It's just I'll talk to you later.
Okay. Yeah. So very good point. So we will be covering Laplace. I mean soon. We will be. I mean all of these problems we can solve with the help of the Laplace. But here we are learning that RLC transient circuit. So we will be solving in that way. Our next chapter will be a single phase AC circuit. Right after that, we will jump into Laplace transform. So we will see how we can solve problem with the help of Laplace. So
Okay, yeah.
of course, we will be applying the Laplace, and that is very, very powerful tool. Yeah. We will be learning that one. So at this point, just everybody have a look at this process, how we can apply these techniques to solve transient. Okay, very good. Okay, so then moving forward, as you can see here, because there are two values of S1 and S2, and there is like plus minus, and now R over 2L might be greater than 1 over LC or might be smaller than. So therefore, accordingly, S1 and S2 values could be complex, could be equal value, or could be both could be real value, real and unequal value. So depending on an S2 values, again there could be three situations: overdamped case, critically damped response, and underdamped response. This means if alpha greater than omega naught, alpha equal to omega naught, alpha less than omega naught. So depending on three situations, the solutions can be three types. If it is overdamped, then the solution will be this type. If it is critically damped, this is the nature of the solution. When it is underdamped, this is the nature of the response. And then here omega t is called damped natural frequency, which is root over omega naught square minus alpha. So everybody remember, we also exactly did these things in the previous class. So instead of IT, those expression were for VT, because that class we are dealing with parallel circuit. Today we are looking into series circuit. So this means the same thing can be applied for voltage and current calculation. Okay, so therefore based on this information, now let's have a look to numerical example. See this example. If R equal to 10 ohm, L equal to 5 Henry, and C equal to 2 millifarad in the following circuit, find alpha, omega naught, S1 and S2. Also, what type of natural response will the circuit have? I mean, is it underdamped, is it overdamped, or it is critically damped? That's the question. And find out those alpha, omega naught, S1 and S2. So I have written down the answers here, but next slide, let's have a look the solution. Let me make it big little bit. I think it is much clear now, right? Yes. Okay. So everybody say, first I am calculating S1. So what is S1? Minus alpha plus root over alpha square minus omega naught square. And here is the S2 expression. Minus alpha minus root over alpha square minus omega naught square. So then what is alpha? Alpha is R over 2L. And then R value was given, L value was given. Substitute those values, you are getting alpha 1. And then find out omega naught. What is omega naught? 1 over root over LC. So therefore again substitute the value of L and C. Finally you are getting 10. So you see, and clearly the alpha is less than omega naught. This is 1, this is 10. So when alpha is less than omega naught, this means that is the, you see, we look the underdamped response. This is the conclusion. So therefore here we go, at last I have written, since alpha less than omega naught, the circuit has underdamped response. That was the question. And also the question was find out S1 and S2, those two natural frequencies. And then I already have written down the expression of S1, S2, just substitute those values. You already calculated alpha, omega naught, just plug in those number into this expression. So you are getting S1 and S2. And as you can see, it is plus j or minus j. This means those are the complex number. Now, I mean, you might use the symbol I sometimes, in some math book or even circuit books, instead of symbol J, symbol I may be present, or you might use that. That's also fine. Just remember, this is the complex number. So everybody, could you follow me?
Yes.
Yes.
Yes, great. Yeah. So therefore, as I already told, I am going to assign the first set of by the end of today. So again, you will be looking something similar, not exactly the same, but very similar problem. You all need to apply all of these techniques to solve those problems, homework problems. Okay, very good. Let's move to the next problem. Okay, so in this case, what was the problem? For the following circuit, find out VT, and this means voltage across capacitor, for t greater than 0. So everybody look the circuit. On the leftmost side, there is a 3 ampere current source, and initially the switch was closed. It is showing that at t equal to 0 time, switch is getting opened. So this means initially switch was closed. And then there is 20 ohm resistance, in parallel 10 Henry inductor, in parallel 4 millifarad capacitor. So the question is find out VT. So at the bottom I have written down the answer. So everybody see, in this case, that initial conditions are not mentioned. So this means at first you have to find out the initial condition. And you need two initial conditions. Always keep in mind, you need two initial conditions, one for current and other for voltage. This means that how to find out the initial conditions? Assuming that initially this switch was closed. So therefore everybody see, when the switch was closed, this means this 3 ampere as the main source that is flowing 3 ampere, uh, and then 20 ohm resistance. But because this is inductor, the middle component, and you know that 3 ampere is the DC current. So therefore for DC, 10 Henry will be short circuited, and then capacitor will be open circuited, but the 10 Henry inductor will be short circuited. Therefore, how much current will flow through the inductor? Could you answer? How much current will flow through the inductor?
3 amps.
Exactly 3 amp. When no current will flow through the resistance. You see, therefore, see my pointer, 3 ampere will go. Nothing will enter into 20 ohm because it is already short. So all the current will go through the inductor. And this is already the open. So this will be the flow. So it will be the flow. So therefore, great. So you got that this is 3 ampere. And then what will be the voltage across the capacitor under that condition?
0 volts.
0 volt. Great. Yes. Because although it is open, but it is shorted. So this means it will appear 0 voltage here. So great. So those two are the initial condition. So great. So therefore, everybody see in the next one, next slide. Yes, here. Uh, so first I did that. See the solution. When switch is closed, this means I naught equal to I naught 3 ampere that we already discussed. And then V naught equal to capital V naught 0 volt. Now these two are my initial condition. Now see the circuit. This is my circuit. At t equal to 0 time, the switch is getting opened. So if at t equal to 0 time, switch gets opened, then how does the circuit look like? Because the now 3 ampere source is getting disconnected. So therefore these three components will be in parallel. So therefore 20 ohm and 10 Henry and 4 millifarad will be in parallel. So therefore this is going to be a parallel circuit. Therefore the circuit that we discussed in the previous class. So I mean it depends on the circuit. After eliminating the source, it might be converted into, or it might look like series circuit, it might be parallel circuit. So it does not matter, because by now you all have already learned how to solve. So accordingly you choose the equation and solve it. So therefore methodology, everything is the same. Only thing is that alpha value is different. You see, in case of parallel circuit, alpha is 1 over 2 RC. But today we looked, in case of series circuit, alpha is R over 12. Only that's the difference. But omega naught expression is the same. Your response solution is the same expression. Only the alpha is the different in case of parallel and series circuit. Okay. So because this is parallel circuit, so my alpha is 1 over 2 RC. Now I am going to the solution. So what was my question? My question was, I have to find out the VT, voltage across capacitor, for t greater than 0. So now I am doing that. So first I found out the alpha, and then I calculated omega naught. So everybody see, alpha is greater than omega naught. This is 6.25, but this is 5. Now because alpha is greater than omega naught, so the response should be overdamped. Because the response is overdamped, so then accordingly choose this expression. You see, Vt on multiplied by e to the power s on t plus a2 e to the power s to t. This is my general expression. Now there are four unknowns, s on s2 and a on a2. So therefore first find out s on and s2. So this is the s on. So S on needs alpha and omega naught that we already calculated. Just plug in those numbers. So you are getting minus 2.5. And here S2 is minus 10. Now substitute S1 and S2 in this equation. So after substituting S1 and S2, is still, you see, there are two unknowns, two constants, A1 and A2. That we have to find out. with the help of initial conditions that we did at the top. So far everybody, could you follow me?
Yes.
Oh,
Yes.
okay, thank you. Okay, then now moving forward. Okay, see, so then that was my expression Vt on e to the power s on t, but I substitute the value of s on, that is minus 2.5 t, and then s2 value was 10, so I put that on e to the power minus 10 t. Now your goal is to find out a1 on a2 with the help of those two initial conditions. So now everybody see, at t equal to 0 time, so look this expression, at t equal to 0 time, v naught equal to 0. So how I get that on? You see, from here, we already calculated at the beginning, v naught equal to capital V naught, which is 0 volt. So therefore, that is 0. But then in this equation, put t value equal to 0. So therefore, you are getting a1 because this will be 1. Similarly, e to the power minus this will be 1. So a2. So this means a1 plus a2 equals to 0. Therefore, from there, I am just writing a2 equal to minus a1. You might do other way, a1 equal to minus a2. It does not matter. Still, you will be getting the same result. Okay, then now come back again, dv naught by dt. Now, can you remember this expression? The previous class, we derived this one from equation J, we derived, and can you remember what I am talking about? There was one special expression that you need to use. So this is dv naught by dt minus ri naught plus v naught over rc. So this came from the parallel circuit. I mean, today we derived a different expression, but because this problem is related to parallel, automatically it came. And then plug in those numbers. R value 20, and then I naught value is 3, V naught value is 0. These are coming from the initial conditions. Look that up, I naught value is 3 and V naught value is 0. So, and then in the denominator, R value and then C value. So from here I got minus 0.75. I just expressed in that way. I mean, you may write down minus 0. Oh, sorry, you can write 75 or 750, but I just wrote in that way, minus 0.75, 10 to the power 3. Now, again from equation A, make its time derivative, dv by dt. So see this one, a on, and then for this one, minus 2.5, e to the power minus this one. And then from here, this is that minus 10 is coming from here, so minus 10 a2, e to the power minus 10. Just time derivative, first derivative. And then why I did that? Because this is dv0 by dt, we calculated. Now in this expression, make dv naught by dt. So dv naught by dt, this means this on, and then from here you are getting this portion is 1, so minus 2.5 a1, and here minus 10 a2. And then just apply the algebra after that. And apply this one, a2 equal to minus a1 that I derived there, so that it will be all a1. Finally, I am getting a1 value is minus 100 and a2 value is 100. So therefore, that is equation A was my solution. So substitute the value of a1 and a2 that you obtained in this equation. So finally, this is your result. Is everybody fine?
Yep.
So just the tricky part is this part. I mean, this part, if you can solve carefully, then you are fine. So therefore, just the key is that, I mean, here is the step. I mean, what you will be doing, if initial conditions are given, then you are fine. like you are done one step. If initial conditions are not given, then at the beginning find out initial condition. That should be your very first task. Next task will be, after considering any condition, in this case like switch is getting open, this source is getting disconnected, redraw the circuit. How does the circuit look like? Okay, and then once you do that, because you have to pick up an appropriate equation corresponding to the response, you have to determine whether it is overdamp, underdamp, critical damp. That's why after drawing the circuit, next step will be finding out alpha and omega naught, because you have to make a comparison. Once you find out that, just compare, is it equal or unequal, or this is small or this is greater. Depending on that, you choose the appropriate equation, and then find out the S1, S2, plug in there. And once you do that, then rest of the thing is just applying the initial condition to get the two constant A1 and A2. So everybody just remember the steps, how to move forward. So this is a little bit tricky part. If you make mistake here, calculation, then you will be getting different result. But as long as you are following this process, I think you will be fine. So therefore, you see, after writing this expression, you have to write down dv by dt expression. Just keep in mind. And then from on initial conditions, you can easily apply on initial condition. For example, in this case, V0 was 0. So easily you are getting that on. And you got A2 minus A1. I mean, depending on problem, this could be different expression. And then once you get that dv by dt of that one, again make dv naught by dt, and then make a comparison and use this expression in case of parallel circuit. In case of series circuit, use a different expression and then plug in that one. And then next is just the algebra, simple calculation. If you don't make any mistake in anywhere, then you will be getting the proper values, and then substitute those two constant into the main equation. That's all, then you are done. Any questions from anybody? So therefore today, as again I am telling that in the first set of homework, you will be looking similar problems. One or two could be a little bit complicated than this, but if you just follow this class and then previous class, I believe everybody, each of you will be able to solve all the problems in the homework. Okay, and then moving forward. So let me a little bit. Okay, here you see a little bit different topic, step response of a series RLC circuit. So far we looked source-free series circuit and source-free parallel circuit. But in this case, it is a series circuit. But can you see, at t equal to 0 time, a DC voltage source is getting connected, like a step voltage source, Vs, at t equal to 0 time. This means initially it was source-free circuit, and suddenly you are connecting a source. Then what? Then how does the response look like? That's why it is called step response of a series RLC circuit. Now, because this is a series circuit, so I current is flowing and the voltage across capacitor is V. So therefore, you know, in these cases, the main concentration will be capacitor and inductor. In case of inductor, always you have to find out the current, and in case of capacitor, mostly you have to find out the voltage. And I mean, you might not be asked any question about resistance, because these are the two components that can store energy even though there is no source. That's why these two components are of paramount importance. Okay, now based on this circuit, look this one. So this is my circuit. Now write down the voltage expression. Apply the KVL in this case. So you see right side that Vs, and then Ri plus LdI by dt for capacitor on over say integration of T naught to T I dt. Now from here, what I am getting Ri, then I am writing this on LdI by dt, and see this one, this is actually the voltage across the capacitor. So that's I replaced this expression, middle expression by V and Vs. But here you see, because suddenly we connected this source, then what is the current expression? So the same current will flow through inductor and then capacitor. That's why I have written, but IC equal to C dV by dt, which is equals to I. Now substitute this I value in this expression, in expression A. So what we are getting? R for I C dV by dt. So CV by dt, L d by dt. I value is this one. This is plus V and then this is Vs. Then this is RC dV by dt. So look the middle term LC d square V by dt square and then Vs. So this means because there is d square V by dt square, I mean I am rearranging here. So this means this is again clearly the second order differential equation. This means this is second order circuit. Now one important thing, I mean each of you have done these things in math class. For this type of differential equation, for the solution, there will be two parts. One part is called VT is called transient response plus VSS. SS is called steady state response. I mean there are two parts: transient part or natural response part, and steady state or forced response part. In the solution, there will be two parts. So therefore, everybody make a comparison. The problem that we discussed so far in previous classes, always it was source free. There was no existence of Vs or the current. Yeah, it was source free. That's why we did not take care of the second part. That is our solution. Vt equal to Vt, or whatever this format is, like overcurrent, over damped, under damped, or critically damped. This is that thing. But today we are adding another term, VSS, which is the steady state response. This means that look the circuit. Once you are connecting the DC source, suddenly at t equal to 0 time, and then wait a long time, I mean infinity time, what should be the voltage across the capacitor after a long time?
Yep. Or should be max. Be
E-
oh.
Exactly. So this voltage, right? So this voltage will appear after a long time. That is the value of the VSST. So therefore, when you will be solving numerical problem, just by looking the circuit, what is the final value or what is the value of the voltage across capacitor at infinity time? That is the meaning of the second term. And then the first term is as it is that we have discussed so far, overdamped, underdamped, or critically damped. So that's why, based on that, in the next slide, everybody see I have written here VSST is Vs at V infinity time. That is the meaning. And then the other response, the response for the first part, transient part is either of these three terms, overdamped case or critically damped case or underdamped case. Choose the equation based on the value of alpha and omega. So therefore, what will be the final solution? You will just be adding that part, this thing, VSS part. That is VSS plus either of these. So this means for this type of case, for this type of circuit, process is exactly the same. Exactly you will following the same process, whether it is parallel circuit or series circuit. Just you have to add a new term because there is source present now. What is the final value or steady state value due to that response? That's why it is called step response of a series circuit. Okay, therefore now look how it will be the situation in case of parallel. Now this is the step response of a parallel RLC circuit. So therefore, in this case, again, the assumption is that there was a parallel source-free circuit. Suddenly, a current source is getting connected. Like there was a switch here, switch is getting opened. Initially, like switch was closed, so this was sorted out. But then at t equal to 0 time, suddenly we are opening this switch. Because we are opening this switch, this means this current source, DC current source is, it appears across these three components. So then what? Then what to do? So therefore, similarly, again, this is the circuit. So now apply the KCL at top node for t greater than 0. Now this current is entering here, and then current is flowing here through this on and through this on. So therefore, according to KCL, this I is equal to, look this one, we are assuming the voltage here at top node is V. So V over R. We are not writing anything directly, we are writing the I for the inductor. And for capacitor, we are writing IC C dV by dt in that format. But everybody see, for inductor, V equal to L di by dt. So you all know the voltage expression for inductor. Now substitute this one in this equation. So what you are getting? L over R di by dt plus I plus CL, the d square I by dt square equal to I. And then again rearranging that term. So see the expression. Again, this is clearly the second order differential equation. So therefore, what could be the solution? Therefore, for this type of expression, solution will have two parts, the transient part and steady state part. Again, for the transient part, it could be any of these three situations: overdamped, critically damped, underdamped. And but for this on steady state, for example, for this circuit, what is the final value of current through inductor? So what should be the value here? Steady state value or for a very long time?
Is.
Yes, exactly, because this will be short circuited after a long time. So that's why you see in the solution, IS's value is IS. So the final solution will be IT, IS plus either of these, either this one or this one or this one. It depends on the value of alpha and omega. So therefore, when you see that you are asked to find out the current, exactly follow this process that we have learned and then calculate the final value. So in the previous case, in this case, find out what is the final voltage across the capacitor. That will be VSS. That's all. So therefore, I did not set up a problem, so we don't have much time today. But in the homework, you might say on problem based on this step response of a parallel circuit or step response of a series circuit. So exactly, you all will be utilizing these concepts. So is everybody fine?
Yes.
Okay, great. So I think today I did not set up any further slide. Um, we are almost done of this chapter. So one Monday I will try to finalize this chapter, and then we will jump into the actual AC circuit, single phase AC system, like that sinusoidal current response or the voltage response, which is actually the AC. Like, you know, at your home, it is the AC, it is not the DC. So we need to understand, we need to learn the characteristics, dynamics of the AC system. First, single phase AC system, and at the end of the semester, I will take you to the three phase system. Like in real practice, when initially voltage built up, power is built up, that is the three phase. And then finally at our home, it is the single phase, one phase and neutral system. But in real practice, in real power plant, it is three phase. So at the end, we will be learning the three phase. And then as someone was telling, Laplace, right after that chapter, AC circuit, I think we will be spending 1 more week. Then probably around first week and second week of September, we will be extensively covering the Laplace transform. So that, and probably I think you are taking the signals and system course, right?
Yes.
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 I think there the professor will cover the Laplace some sort, and also in math you might have covered the Laplace as well. But we will be applying the Laplace knowledge into the circuit problem. We will be solving this type of problem with the help of Laplace, because Laplace makes our life easy. I mean, easy, and you will be see the beauty of essence of using Laplace. You are not worried about the initial condition. Automatically, it will be taken into account. Here, like, because there are initial condition, like you are utilizing this type of the concept or this type of knowledge, but easily you can do with the help of Laplace. But that's a different chapter. So in 2 weeks we will be jumping there, so everybody will be fine. Okay, so is there any questions, comments from anybody? So the other thing is that how are you understanding these codes? I mean, I understand that this first chapter a little bit complicated. Suddenly it is the transient transient RLC circuit. But then I believe the next chapter you will get more fun, and that will be much easier than this one, the single phase AC circuit, and then followed by all. So far, how do you feel? Do you feel it is complicated, or you're fine?
Feel like you just have to memorize the steps and then every problem should be easy.
Yeah, right. In the world, in real practice, everything is easy, everything is complicated. So it depends on how you interpret and how you take the things and solve the things. No problem is difficult. Again, no problem is easy. Like you see, it depends on your understanding, your following the process, and that memorizing the step. That's all. Then you will feel good. Just as I told you, a little bit complicated this chapter. So I'm going to assign you the homework. When you will be solving the homework, you'll say sometimes you might need some long calculation, but then just be patient and you will be fine. But I believe you will be learning a lot. And as I told you, like from next chapter, you will get fun. You will learn a lot, and I will make it fun for you. And then just the other question that like, am I going fast, or this space is fine for you?
The space works.
Okay, great. Yeah. So, yeah. Okay then. So thank you everybody for joining, and then wait until around evening. First, I will be uploading the homework, and then I will sending an email, and then you start solving. And as I told you, the due date is next Friday, so you are getting about 7 days, so you will be fully fine. On or two problem, it might be difficult, but on Monday I will be covering something, especially the problem related to this and a little bit different. And then after Monday, you all will be able to solve all problems. So you might see 5, 6, or up to 7 problems in the homework set 1. Okay, so with that, let me stop sharing. So thank you everybody